All right, so let's go over the basics. All right, so what I'm going to do is I'm going to just test you underneath this law. So this test is not going to be as bad. Conceptually, it's not going to be as bad. Mathematically, it's not going to be as bad. All right, let me just go over the basics. The purpose of this observation is to the question of unstrapped objects inside vehicles, right? Why do they move in the opposite direction of the acceleration of the vehicle? All right, so the car changes direction, that's acceleration. So the unstrapped objects will move in the opposite direction. You accelerate, speed up. All right, so once again, they're going to move in the opposite direction of the acceleration. You put the brakes on, the car is slowing down. Now the unstrapped objects will move forward. All right, so we knew that from the first week on. So the question is, what's causing these objects to move in the opposite direction of the acceleration of the vehicle? Head-on collision between a car and an SUV. All of these are conceptual test questions, by the way. I'm kind of giving you the answers. All right, so which one experiences a larger impact force? Is it the car, is it the SUV, is it the both? And how do you justify it? All right, so you know that the SUV is going to be better off, the car is going to be worse off. And you're going to think to yourself, oh, the car is going to be worse off because of the simple reason that, you know, it experiences larger amount of force. That's common sense. Both vehicles will experience the same force. If so, why is that the SUV is better off, the car is worse off? All right, so that's one of the questions that you will have to answer on this answer. All right, so what's pushing them out of the boat? All right, notice that they get projected or ejected from the boat, and they will go flying. This projectile motion. So horizontal motion, the speed along the horizontal direction is going to be constant, right? So what's pushing them in the direction of motion? The answer to that question is nothing, right? The boat ended up changing direction. They just maintain their initial motions. Right? So that tendency to maintain initial motion is known as inertia. So nothing is pushing them. Nothing is pushing or pulling them. They are just simply maintaining their initial motions. The boat changed direction. They did not. Their bodies kept on moving. All right, so that's an example of inertia. All right, so inertia is the tendency to retain initial motion. Motion means velocity. So in the absence of an external force, like a pull or a push, object which is in motion is going to remain in motion, and the object at rest is going to remain at rest. So unless you pull or push on it something, object is not going to speed up. It's not going to slow down. It's not going to change direction. Or if it's at rest to begin with, it's not going to move. All right, so it's common sense. All right, so Galilei is the guy who came up with this. So the mailbox retains its initial motion, or is trying to retain its initial motion. And the object in motion is going to want to remain in motion. Now, this little video packs a lot of physics. All right, and we will find some of the answers from this video. Number one, this person is able to keep up with the vehicle, despite the fact that he's not in contact with it once he's airborne, once he jumps. It's because horizontally, he's maintaining his initial motion, right? The only force acting on him is air friction at this point is 30 miles per hour, so it's not going to have a noticeable impact. If the car is going at 30, he's going to keep on moving at 30 horizontally until he touches down. All right, so what would happen if the car were to speed up though? So relative to the car, it's going to be moving backward, right? If the car accelerates forward, relative to the car is going to move backward. Okay, nothing is pushing him in the backward direction. He's simply maintaining his initial motion, right? Because there's no way for him to be able to keep up with the car unless there's a push in the forward direction. If the car is accelerating, he won't be able to keep up with it. Relative to the car, he's going to move in the opposite direction. So that's the answer to the question of the objects moving in the opposite direction of the acceleration of the vehicle. They are moving in the opposite direction because they're simply maintaining their initial motions. What would happen if the driver pushes the brakes on when this guy's airborne? All right. So what's going to happen is the car is going to slow down relative to him, which means that relative to the car, this guy is speeding up. He's moving relative to the car, he's moving in the forward direction. Let's put it that way. So which means that he's going to be moving in the opposite direction of the acceleration of the car if the guy puts the brakes on. So the same thing happens to the objects inside, right? If they're not strapped on, they're going to move in the opposite direction of the acceleration of the vehicle because they're simply maintaining their initial motion. So the next question is, so the objects will move in the opposite direction of the acceleration of the vehicle. We get that, but why do you feel a push? Because literally, when you are wearing a seatbelt, you will feel a push from the seatbelt. When the car accelerates, you feel a push in the forward direction. What's generating the push? What's going on? And then what's generating the push? The reason why you end up feeling a push in the opposite direction of the motion, it's not necessarily because there's a force acting on you, but because your body simply is trying to maintain its initial motion. All right, and how much it wants to maintain that initial motion is known as your mass. All right, so you end up getting that push from your mass because your body is going to resist change of motion. The mass is going to resist change of motion. So that's what happens. So inertia is something that you get from your mass. The bigger the mass is, the bigger the inertia is going to be. So the mass is a measure of inertia, expressed in terms of kilograms, proper unit to slugs. In the United States, instead of using slugs, we use pounds. So the mass is expressed by its weight in the United States. Okay, so this causes slight problems in terms of the understanding and appreciating the concept of mass. Because a lot of you guys mistakenly thought, and hopefully you're not thinking that way at this point, you thought that if something is weightless, it's also it's massless. Okay, so if I were to take a super tanker, which is about 330 million pounds, take it out into deep space, where it's perfectly weightless, where it's gonna weigh less than a penny. Can you move it by pushing it or pulling it? Can you just move it around at will? Right? A lot of you initially thought that, yeah, you should be able to because it's weightless. Only to realize that just because something is weightless does not mean that it's massless. Mass is a measure of inertia. That's the measure of the tendency of an object to want to remain at rest or to want to remain in motion. All right, so if it's extremely massive, it's going to offer a lot of resistance to change in motion. So the thing that you cannot move here on Earth because it's really, really, really heavy cannot be moved in space either. All right, so hopefully you guys made that connection because obviously I'm going to explore your understanding regarding the difference between mass and weight. All right, so anything and everything that I discussed in the lectures, obviously these are fair test questions. All right, so first law is what happens in the absence of an external force, net external force. The second law is all about what happens in the presence of a net external force. If there's a net external force, the force is going to overcome inertia, and which means that it's going to cause an acceleration, right? So force acting on the mass is going to cause it to accelerate. So we got this force acting on this mass, it's going to cause it to accelerate. The proper unit is going to be newtons. All right, so crash testing, 40 miles per hour. The vehicle is moving at 40, dummy is moving at 40. Crash, notice that the dummy gets projected in the opposite direction of the acceleration of the vehicle. The vehicle is slowing down. Dummy looks like it got pushed in the forward direction. In reality, what's happening is the dummy is retaining its initial motion all the way up to the dashboard. So the dummy is going up to the dashboard at 40 miles per hour, right? It's maintaining its initial motion, but as soon as there's a force acting, what happens? All right, so that force overcame that inertia, that tendency, right? The dummy slowed down, it changed direction. Okay, so the external force causes you to speed up, slow down, or change direction, which means that the external force is going to cause acceleration. All right, so now we will do a compare and contrast to the next scenario. It's exactly the same. Imagine that you got a baby sitting along without a seatbelt, or a child or a baby being held by an adult who's not wearing a seatbelt. In which scenario the child is going to be more dangerous? All right, so sitting alone without a seatbelt versus being held by an adult who's not wearing a seatbelt. Okay, so intuitively you know the answer. The scenario is more dangerous. Okay, so, and then if this were a test question, at that point the confusion starts because how do you explain or justify that the scenario is more dangerous? Okay, so I'm not necessarily interested in poetry. I'm interested in a solid explanation based upon physics. So the explanation that I'm looking for is the following. All right, so let's do a compare and contrast. Both of them are 40 mile per hour crash testing. This scenario versus this scenario. This is a lot more dangerous. Why? Because now you're dealing with a combined mass, meaning that this has a lot more inertia, right? The combined mass is going to have a lot more inertia. So it's going to require a lot more force to bring that mass to a stop. So this is going to require a lot more force to bring the combination to a stop because you have to overcome that inertia. So when you have a baby and an adult, now you have to bring the combined mass to the stop, which means that you have to overcome the inertia of the combined mass. That requires a lot bigger force to bring the combination to the stop. As a result, this one is going to cause a lot more damage. All right, so the conceptual questions are like this. And notice that I'm not using my opinion. I'm just stating the facts and using the concepts. The concept of inertia is important here. So the bigger the mass is, the more force is required to bring the combination to the stop. Because you have to overcome that inertia. All right, so deep space. Let's use the example of that super tanker, which is 330 million pounds. It's perfectly weightless. You're also weightless. Right? You don't have your footing this time. You just push it against the spacecraft. So will it move? Commonsensically, you will say no, because now at least you got the concept of mass, right? This thing is extremely massive, 330 million pounds of mass. It's going to give you 330 million pounds of resistance to change motion. Will it move? In theory, it should. In reality, you won't be able to see it, but in theory, it should. How so? Because if there's a force acting on anything, it doesn't matter how big the mass is. If you apply a force on it, it should accelerate. Because net force, if there's any force acting on it, it should overcome its inertia of that mass. Tendency of that mass. What's the amount of force that you can apply maximum? I don't know. Maybe slightly more than your own weight. All right? I'm just like, whatever it is that you can bench press. That's 250 pounds, 200 pounds. I don't know what it is. So you push against it for a fraction of a second. something which is 330 million pounds, right? All right, so you got a small amount of force on something which is really massive, which means that the acceleration is going to be unnoticeably small. All right, so it's going to move in theory, but it's going to be microscopic. You, on the other hand, will get propelled in the opposite direction, propelled. You push against it with a 200-pound force, and then you'll go from 0 to 5 miles per hour. So you will accelerate in the backward direction. So that implies that there's a force acting, right? So the question is, where does that force come from? Your initial reaction is you're getting the force from your muscles, but that's a bad answer because according to Newton, the force responsible for acceleration has to be external to your body. And if you're thinking about how's that, just think of it this way, guys, just like lifting yourself up. Can you just grab the other arm and lift yourself off the ground by pulling on yourself? The answer to that question is no. So internal forces cannot cause acceleration. Right? Just let that sit in for a while in your heads. All right, internal forces will not cause you to accelerate. So the force responsible for the acceleration has to be external to your body. All right, so all of a sudden you go, okay, so you apply a force on the spacecraft. So this force is the action force responsible for the motion of the spacecraft. In turn, you will experience the same force acting back on you from the spacecraft. So this is known as the reaction force. All right, so Newton will say the forces will come in pairs. So for every single action force, there's going to be an equal and opposite reaction force. All right, so the forces are equal, they're in opposite direction. Okay, so far I'm kind of summarizing the lecture, but let's just add on a little bit because on the test also I have these weird mind twisters that you don't see coming. I also explore your blind spots on the test. Okay, so there's a bit of a blind spot that I left here on purpose that I would be exploring on the test. So just to see the A students and B students and be able to distinguish the B students from C students. Sometimes it's intentional. All right, so let me just point out something here. Let me just give you a question, just something to ponder just briefly before I answer the question. You know that the action and reaction forces are the same, right? Whatever the force acting on the spacecraft is exactly the same force acting on the astronaut, right? All right, so these forces are the same. They got the same magnitude, they're in opposite directions, right? Given the fact that the action and reaction forces are the same, how much force is required to actually move the spacecraft? Okay, so imagine that the spacecraft is my Fort Temple, all right? It's, I don't know, it's like 2,000 pounds in space. You can literally push it. So how much force do I have to apply on the Fort Temple in order to make it move relative to the reaction force that I'm experiencing? Okay, so the amount of force that I'm applying on the Fort Temple, should it be larger, the same, or smaller than the reaction force that I'm experiencing? Remember, guys, action and reaction forces are the same, right? They're in opposite directions. Now, for the Fort Temple to move in space, how much force do I have to apply relative to the reaction force? All right, so the force that I'm applying on it, is it going to be bigger, smaller, or is it going to be the same as the reaction force? I just think about it, just briefly. Don't answer it, just think about it, because I know what you guys are thinking. All right, now that you guys thought about it, let me add on to it. You know the action and reaction forces are the same, right? If they are the same, will the Fort Temple ever move? If the amount of force that you're applying on the Fort Temple, if it's the same as the amount of force that the Fort Temple is applying back on you, given the fact that the forces are the same, wouldn't the forces cancel out? Doesn't that mean that you should apply a larger force on Fort Temple than the amount of force that the Fort Temple is applying back on you? And most of you guys will say yes to that. That's kind of weird. And this comes about because of the lack of understanding of the third law. Third law is kind of tricky. Guys, what is the amount of force required to actually move Fort Temple? Any force is going to move. Any net force acting on Fort Temple is going to cause it to accelerate. Action and reaction forces are the same. They're not applied to the same mass. Therefore, they would never cancel. All right, so any net force acting on the Fort Temple is going to cause it to accelerate. Any net force acting on the supertanker is going to cause it to accelerate. How much it's going to accelerate depends on the mass. Fort Temple is not as massive. The acceleration is going to be noticeable. Supertanker is extremely massive. Acceleration is not so much. All right, so any net force acting on the Fort Temple or the supertanker is going to cause them to accelerate. The reaction force is acting on you. All right, so the action and reaction forces are not applied to the same mass, so they would never cancel out. So any net force acting on you is also going to cause you to accelerate. So you push up against the Fort Temple, which is 2,000 pounds. All right, you're less massive than a Fort Temple. Your acceleration is going to be much more noticeable than the Fort Temple. So you will get propelled back in the opposite direction. The forces will not cancel because they're not applied to the same mass. All right, so that's once you make that connection, the rest is actually straightforward. All right, so we will explore that connection as well. All right, so the head-on collision between a car and an SUV, which one experiences a large impact force? It's the same. It is the same. Both of them will experience exactly the same impact force, except force is the same. SUV is more massive, so the acceleration of the SUV is going to be smaller. Remember, acceleration is what kills you, what maims you, what breaks your bones. Smaller acceleration makes it much more survivable. And the car is not as massive, so the acceleration is going to be greater. Smaller mass, greater the acceleration, so it becomes more dangerous. All right, so head-on collision between a car and an SUV, you don't want to be the car driver. Absolutely not. A smart car, forget it. All right, less massive the vehicle is, the bigger the acceleration is, so it makes it more dangerous. Smart car going up against the bus, even worse. All right, you're inside the bus, you're fine. A smart car driver, not so much. Smaller mass, the bigger the acceleration is. In case taken to an extreme, person getting hit by a train. All right. Will the person apply the same force back on the train? The answer to that question is absolutely yes. So where's the evidence? Once again, it's a test question. So no one denies that a train can apply like 1,000,000 pounds of force, large enough to break you apart. Where is the evidence that the person applies the same force back on the train? So that becomes a test question. All right, it's the same force applied back on the train, except the train is real massive. Right? Bigger the mass, the smaller the acceleration is. It so happens that the train is so massive that the acceleration is going to be unnoticeably small. All right, so the numbers still will work out. All right, so let's go into the basics for this one. Okay, what is it that I want to do? I don't want to do this one. All right, so the inertia is the tendency to retain initial motion. Motion means velocity. Velocity is a combination of speed and direction. So what that means is the object in motion is going to have a tendency to remain in motion, meaning that it's going to have a tendency to go in a straight line at a constant speed in the absence of a force. If it's at rest, it's going to remain at rest. Okay, so the objects will get that tendency from mass. So the mass is going to be the measure of that inertia. So it's going to give you a number. The bigger the number is, the larger that tendency is. All right, Geller is the guy who came up with that, and that later becomes Newton's first law. And Newton's only contribution is to explain where that tendency comes from. He said you get that tendency from mass itself. Proper unit is kg or kilograms. In the United States, we use pounds. Conversion factor is something you can get from the formula sheet. So it's 1 kilogram is going to be 2.2 pounds. And then we got the second law. The second law is all about what happens in the presence of a net force. So if there's a net force acting, the net force is going to overcome the inertia, meaning that if it's acting on an object, it's going to make it go faster, slower, or it's going to make it change direction in the direction of that external force. Proper unit is newtons. In the United States, we use pounds. So for mass as well as the force, we use pounds. So the conversion factor is 10 newtons, roughly 10 newtons is 2.2 pounds. All right. If the car is speeding up, there's enough force acting on it because the car is accelerating. If the car is slowing down, there's enough force acting on it because the car is still accelerating. If a car is moving on a curve at a constant speed, there's enough force acting on it because it's still accelerating. Third law is all about how these forces come into existence in nature. So it says forces will come in pairs, so there will always be force pairs. One force is going to be responsible for creating the pairs that's known as an action force. For every single action force, there's going to be an equal and opposite reaction force. Head-on collision between a car and an SUV, which one experiences a large impact force, so both will experience the same impact force because of Newton's third law, which means that the forces will come in pairs. So for every single action force, there's going to be an equal and opposite reaction force. So a person getting hit by a train with 500,000 pounds of force, will the person apply the same force back on the train? The answer to that question, yes, of course, because of Newton's third law. So on the test, I would say, where's the evidence? And the answer to that question is not much of evidence. All right, so the evidence of a force is acceleration. The train is real massive, extremely massive. It's so massive, in fact, that the acceleration of the train would be unnoticeably small. That's it. It would be unnoticeably small. All right, so in terms of problems, I spent a lot of time on the third law. All right, in terms of multiple choice, just focus on problem number 1, 2, 3, that sort of stuff. And multiple forces is net forces here for the next test. This is what happens. All right, so don't worry about page number 2. And talking to college as well as the university physics audience in general. All right, the only one that both classes should be focusing on this problem. All right, if you are a college physics student, all right, I'm more interested in A, B, C, and D. If you're taking university physics, I want you to be able to do E and F as well. All right, so this requires a little bit more work. And if you're a university physics student, obviously 80–90% of your work is going to be in the form of symbolic algebra. College physics, I accept numeric solutions up to a certain point. by university physics students, you just focus on this problem. Okay. All right. So problem number 4 is the one that we'll focus on. That's the only one that you have to worry about. All right. So problem number 4, a couple of perspectives on it. Head-on collision between a train and a person, more like a train hitting a person. It's not a head-on collision. This person is getting hit by a train. So action and reaction forces are the same. And let me just emphasize a point here. These two forces are not applied to the same mass. They will not cancel. If these forces were to cancel, you could literally stand in front of the train and let the train hit you. Right? If these forces were to cancel, the train would come to its complete stop. Upon hitting you, every single person on the train would be dead, and you would be okay. So that's not how it is. Action and reaction forces would not cancel. Action force is acting on the person getting hit, and the reaction force is acting on the train. All right, so they're not applied to the same mass. They're not going to cancel. So action and reaction forces are the same, but the masses are not the same. All right, so the force on each mass is the same. So acceleration depends on the magnitude of your mass, the size of your mass. Right? So smaller mass is going to accelerate more, and the larger mass is going to accelerate less. All right, so the person's acceleration is going to be high enough to kill. Train's acceleration is going to be low enough to be unnoticeable because the train is extremely massive. All right, so conceptually, this is what we get. Okay, so in terms of numbers, if the train is going at 60 miles per hour, train is going to slow down just a little bit. Acceleration of the train unnoticeably small means train is still going to be moving around 60 miles per hour. If it loses anything, it's going to be 59.999 miles per hour. You wouldn't notice that. This train is just going to jerk, or it's just going to vibrate. The person, upon getting hit, is going to go from 0 to double the speed of the train. Acceleration is going to be large enough to take the person from 0 to almost double the speed of the train. That's it. So the train is coming at 60 miles per hour, impact at 60, person is flying at 120 miles per hour. Okay, so those are the expectations from physics, and those expectations will be justified in the future when we get into the concept of conservation of momentum and energy. All right, so I came up with some kind of a hypothetical example of a person getting hit by a train. I got a bunch of numbers. All right, so this is the problem that you need to practice this sort of stuff. And so this approach works well for college students, college physics students, for university physics students. I'm going to give you a problem, and you have to actually do it just symbolically most of the time. So a person and train, so respective masses, 70 kilograms, that's my mass. Train is 3 million kilograms. Train is moving at 68, person is not. This should be the O. Estimated impact time is going to be 100th of a second. So the accelerations of the person and the train, and the final speeds of the person and the train. Okay, let's do the conversions. All right, so force diagram is required for something like that. It's required. Not only is it good for visualization, but it's also required. Action force acting on the person, the reaction force is acting on the train. Action force is going to cause an acceleration, the reaction force is going to cause an acceleration. All right, so every single test is a formatting test. Make sure that you list everything. Step number 1, take your time. All right, take your time, just list, make sure these are known as initial conditions, and every single solution should be carried out using what the initial conditions are, what's given, because the only way you know you will come up with an answer is having your measurables in your final formula. All right. Everything is listed, the conversions are done. All right, so the first question is acceleration. What's the acceleration? All right, so here's what I know. The acceleration is always caused by an external force. All right, so force is what causes acceleration. So I isolate A. Okay, you cannot write this down as a formula. This is the main formula. Okay, so whatever the formula is available from the formula sheet, that's your starting point. That's your toolbar. All right, use the formulas from the formula sheet, not from somewhere else, not from something that you yourself come up with. All right, stick with the symbols, use proper symbols. All right, so A is isolated. Now I can run a numeric calculation on this one. All right, so the action force, reaction force, they're the same. I listed that as well. So this is the action force acting on the person, mass of the person is going to be 70. Boom, boom, boom. It gives you an answer in terms of meters per second squared. I'm moving the decimal to the left. So it's going to be over 500 Gs. All right, so now I can conclude that the acceleration is going to be deadly. How do I know that? I know that because 140 is as far as you can go for a fraction of a second. And this is for a fraction of a second. This will kill this person. So there's no surviving this. I expect the acceleration of the train to be unnoticeably small. All right, so the reaction force acting on the train, so it's negative. Mass of the train is a mass of 3 million. It's like almost 9 million pounds. All right, so the acceleration of the train is going to be extremely small. I'm not going to even worry about converting to G's. You're not going to notice something like that. Next question is, what is the speed of the person in the train? I picked this formula. Okay, now this requires a justification on the test. Why would you use this formula when there are some other perfectly good formulas available for acceleration? You cannot use any other formula but this one because it's impact. You're studying impact, and impact acceleration changes. All right, acceleration changes during impact. It'll give you a variable acceleration, otherwise known as jerk. Every time something gets hit, the acceleration is going to keep varying within this impact time. So which means that the only acceleration you can use is an average acceleration. It's an impact calculation. You're dealing with chaos. This person's bones will shatter. All right. The person is going to break apart. That's not predictable motion. All right. You're dealing with chaos. Every time you're dealing with chaos, the acceleration is changing. If the acceleration is changing, use the average acceleration for you. Okay, notice that I justified. It's not like, hey, I was looking at the letters. This says A in it, and other formulas say A in it, but this formula was before the other ones. That's the reason why I picked it. Don't give me that kind of explanation. All right, that's not the explanation I'm looking for. I'm picking a formula. I'm saying, hey, listen, this formula fits in with the scenario that we were studying. All right, so I'll say, hey, it's chaotic motion. It's unpredictable motion. There's jerk taking place here. I'm using the average acceleration formula to estimate the acceleration. That's it. From that, I can figure out the final speed. All right, rest is algebra. Boom, boom, boom. All right, it's a different department. Make sure that you're practicing enough, and physics is a good way to actually practice it. So it's part of your muscle memory, all right? Because it's like touch typing or writing a letter. You don't go and look up the letters from the alphabet. Make sure that it's part of your muscle memory. All right, so the person is not moving. I want to know how fast the person is going to move. Initially, the person is not moving. The initial speed is 0. So that's the acceleration of the person. And the acceleration is going to last only 100th of a second. So those are the numbers. All right, so you multiply, so it's going to give 53.57. All right, so as is, makes no sense to anyone. It's always important that you make sense out of numbers. So meters per second you cannot relate to, but miles per hour you can. So we expect the person to be moving at double the speed of the train. Guess what? It worked out beautifully. It's 120 miles per hour. Train is at 60. Person is 120. What do we expect from the train? Train, upon hitting the person, is not going to accelerate as much. The speed of the train should not change as much. So I would expect the speed of the train to be still around 60 miles per hour, slightly less. Not quite 60, but not significantly less either. It's going to be very close to 60 miles per hour. Except the train has an initial speed. Acceleration is negative. All right. And the impact time is still 100th of a second. All right. So acceleration of this train within this duration is going to get subtracted from the speed. And so it's going to give you a speed less than that. It's going to be 59 point something. All right. Almost 60 miles per hour. It worked out. It worked out beautifully. All right, so mathematically, this is as far as it goes. Okay, so I'm not done yet. There's a few more things that I need to point out, just in case. Okay, so let's get back to the problem. All right, A, B, C, and D for college students. E and F for university students. E and F for university students. Okay, so we already did A, B, C, and D. All right, so for college students, you guys are done. Let's work with the university students for the next couple of minutes. It says that, okay, so let me give you an idea of what this would look like on the test. All right, so just what I'm doing in essence is I'm combining what you guys know from the previous week with this week's lecture. I'm turning this into a sideways projectile motion. So what's happening is this person is getting hit. All right, so the train is going at 60 miles per hour, blah, blah, blah. And this is the center of mass of the person is going to be located here. And I'm giving you the location of the center of mass. Let me just change this a little bit. All right, so the center of mass is going to be located right now. And whatever the speed that the person has at the end of the impact is going to become the initial speed of this person on this direction. So the person is going to be projected in that direction, in the whole direction. And then it turns into a sideways projectile motion. And then what I'm interested in is the distance that the person is going to travel on the whole direction. And the time it takes for this person to travel that distance. All right. And everything is going to depend on the speed. And you need to get this speed from the action and reaction forces. All right, so which means that you should be able to do A, B, C, and D properly, and which means that you need to figure out the speed of the person after the impact. So that becomes the initial speed in projectile motion, and then you should be able to figure out the distance that the person is going to travel and the time it takes for this person to travel that distance. So the time that it takes for this person to travel that distance is exactly the same amount of time it's going to take for the center mass to actually reach the ground. All right, so for university students, I'm combining both of them. And then whatever it is that I'm asking for, so I could ask you the distance or I could ask you the time. I'm not going to ask you both, obviously. There are a number of things that I can ask, which means that you will have to come up with an answer using the initial conditions. You will have to reduce everything into a single formula. It's going to be boom, 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 some Chinese, and then it's gonna look like this. All right. All right, so that's what you need to do. All right, that's a hint for the university physics students. So I'm gonna give you guys an hour, but symbolic work is required. So I just assume that this is your homework and then start working on it as you're getting ready for the test. All right, guys, I kind of went over everything that you need. Oh, hold on. Is there anything else that I forgot? Yeah, just give me a second. I need to look something up. All right, let's do one more discussion. I think there's one more thing that I need to discuss. Is gravity a force? At some point, that question is going to come up. When somebody says, is gravity a force? The answer to that question is not yes or no, obviously. If the answer is yes, if you want to say gravity is a force, you need to justify it. If you want to say it's not a force, you have to justify it. So if somebody says gravity a force, that means that does gravity fit into the definition of a force? Yeah, it depends. It depends on the definition of a force, right? So what's a force do? It causes acceleration. Do falling objects accelerate? Absolutely, they do. So this implies that there's a force acting on the falling object. All right, so which makes gravity a force because falling objects do accelerate. That's it. Next question, does gravity extend all the way out to the moon? Well, it depends. If gravity is a force, does it extend all the way out to the moon? All right, so it depends. What would happen if it didn't? There's the moon. If it didn't extend all the way out to the moon would have gone in a straight line at a constant speed. The moon is moving at a constant speed, but not in a straight line. And you know, in circular motion, the acceleration is directed towards the center of the circle. All right, and acceleration implies that there's a force acting, right, along the direction of the acceleration. So all of a sudden, you can trace this force out to its source, and it looks like this force is also coming from the center of the Earth itself. So you can conclude from this that the gravity extends all the way out to the moon, or at least a force does from the center of the Earth. Okay, so that's it. I kind of covered everything that I wanted to.